So what do the neural networks do exactly in the car? So what we are seeing here is a stream of videos from across the vehicle, across the car. These are 8 cameras that send us videos, and then these neural networks are looking at those videos and are processing them and making predictions about what they're seeing. And so some of the things that we're interested in and some of the things you're seeing on this visualization here are lane line markings, other objects, the distances to those objects, what we call drivable space, shown in blue, which is where the car is allowed to go, and a lot of other predictions like traffic lights, traffic signs, and so on. Now, for my talk, I will talk roughly in 3 stages. So first, I'm going to give you a short primer on neural networks and how they work and how they're trained. And I need to do this because I need to explain in the second part why it is such a big deal that we have the fleet and why it's so important and why it's a key enabling factor to really training these neural networks and making them work effectively on the roads. And in the third stage, I'll talk about vision and lidar and how we can estimate depth just from vision alone. So the core problem that these networks are solving in the car is that of visual recognition. So for you and I, this is a very simple problem. You can look at all of these 4 images, and you can see that they contain a cello, a boat, an iguana, or scissors. So this is very simple and effortless for us. This is not the case for computers. And the reason for that is that these images are, to a computer, really just a massive grid of pixels. And at each pixel, you have the brightness value at that point. And so instead of just seeing an image, a computer really gets a million numbers in a grid that tell you the brightness values at all the positions.
A matrix, if you will. It really is the matrix.
Yeah. And so we have to go from that grid of pixels and brightness values into high-level concepts like iguana and so on. And as you might imagine, this iguana has a certain pattern of brightness values, but iguanas actually can take on many appearances. So they can be in many different appearances, different poses, in different brightness conditions, against different backgrounds. You can have different crops of that iguana. And so we have to be robust across all those conditions, and we have to understand that all those different brightness patterns actually correspond to iguanas. Now, the reason you and I are very good at this is because we have a massive neural network inside our heads that is processing those images. So light hits the retina, travels to the back of your brain to the visual cortex, and the visual cortex consists of many neurons that are wired together and that are doing all the pattern recognition on top of those images. And really, over the last, I would say, about 5 years, the state-of-the-art approaches to processing images using computers have also started to use neural networks, but in this case, artificial neural networks. But these artificial neural networks, and this is just a cartoon diagram of it, are a very rough mathematical approximation to your visual cortex. We really do have neurons, and they are connected together. And here I'm only showing 3 or 4 neurons in 4 layers. But a typical neural network will have tens to hundreds of millions of neurons, and each neuron will have 1,000 connections. So these are really large pieces of almost simulated tissue. And then what we can do is we can take those neural networks and we can show them images. So for example, I can feed my iguana into this neural network, and the network will make predictions about what it's seeing. Now, in the beginning, these neural networks are initialized completely randomly. So the connection strengths between all those different neurons are completely random. And therefore, the predictions of that network are also going to be completely random. So it might think that you're actually looking at a boat right now, and it's very unlikely that this is actually an iguana. And during the training process, really what we're doing is we know that that's actually an iguana. We have a label. So what we're doing is we're basically saying we'd like the probability of iguana to be larger for this image and the probability of all the other things to go down. And then there's a mathematical process called backpropagation, stochastic gradient descent, that allows us to backpropagate that signal through those connections and update every one of those connections. Just a little amount. And once the update is complete, the probability of iguana for this image will go up a little bit. So it might become 14%, and the probability of the other things will go down. And of course, we don't just do this for this single image. We actually have entire large data sets that are labeled. So we have lots of images. Typically, you might have millions of images, thousands of labels, or something like that. And you are doing forward-backward passes over and over again. So you're showing the computer, here's an image. It has an opinion. And then you're saying, this is the correct answer. And it tunes itself a little bit. You repeat this millions of times. And sometimes you show images, the same image to the computer, hundreds of times as well. So the network training typically will take on the order of a few hours or a few days, depending on how big of a network you're training. And that's the process of training a neural network. Now, there's something very unintuitive about the way neural networks work that I have to really get into, and that is that they really do require a lot of these examples, and they really do start from scratch. They know nothing, and it's really hard to wrap your head around this. So as an example, here's a cute dog. And you probably may not know the breed of this dog, but the correct answer is that this is a Japanese Spaniel. Now, all of us are looking at this, and we're seeing Japanese Spaniel, and we're like, OK, I got it. I understand kind of what this Japanese Spaniel looks like. And if I show you a few more images of other dogs, you can probably pick out other Japanese Spaniels here. So in particular, those 3 look like a Japanese Spaniel, and the other ones do not. So you can do this very quickly, and you need one example, but computers do not work like this. They actually need a ton of data of Japanese Spaniels. So this is a grid of Japanese Spaniels showing them, you need thousands of examples, showing them in different poses, different brightness conditions, different backgrounds, different crops. You really need to teach the computer from all the different angles what this Japanese Spaniel looks like, and it really requires all that data to get that to work. Otherwise, the computer can't pick up on that pattern automatically.